And we're right on time. And for our last talk, which is going to be our longer talk, and that is from Akos Ledeczi. And he's going to be talking about his work developing an animal-borne acoustic shockwave detector. So, Akos, whenever you're ready, take it away.
Thank you. Thanks for the introduction. I used to be at Hungary, but now I'm at Vanderbilt University in Nashville, Tennessee in the USA. And this work has been a collaboration with lots of people and institutes, as you can see on the screen. To make sure that I have time for the acknowledgement, I put this slide in the beginning. So this project has been funded by Vodafone and also Vanderbilt University. And these wonderful institutions at the bottom have been helping us to actually deploy and test the prototypes. All right, so what was our motivation to go into this project? Well, of course, we all know that poaching is a problem, so anything we can do to help with that would be helpful. And my group at Vanderbilt has been working on acoustic gunshot detection, classification, and localization for over 20 years. We have been using low-cost sensors, specifically wireless sensor networks. So that was kind of one of the motivations. And we have heard about static deployments of shot detectors to protect wildlife. But the problem with those that they are not scalable. They protect a relatively small area and not necessarily the animals themselves. And then, of course, we have witnessed the proliferation of GPS tracking collars. So out of these four things came the idea of let's create a shot detector that the animals themselves wear, so it protects the animal. So let's talk a little bit about gunshot acoustics. So typically when people hear a gunshot, they hear the muzzle blast, which is basically the propellant of the bullet exploding in the barrel. But if it's a rifle shot, then more than likely it is a supersonic projectile that is leaving that barrel, and the supersonic projectile generates a sonic boom, also called a shockwave, and that can also be detected by the microphone. So if you look at the typical acoustic events when you record a gunshot, the first one is typically the shockwave itself, and the beginning it really looks like an N, a capital N, and it's a very unique event. Then you hear, of course, ground and other reflections, and then eventually the muzzle blast arrives at the microphone as well. But the shockwave is such a unique event that it's easier to detect and classify as a shockwave. So it's a better signal to focus on. So just briefly, what you can do with microphones when a shot is being fired. So here S denotes the gun that's being fired, and then you can see the trajectory of the supersonic bullet, and then M denotes the sensor. So if you have a microphone there, you can detect the time of arrival of the muzzle blast, the time of arrival of the shockwave, and even the length of the shockwave, which depends on the caliber and how far the projectile is from the sensor. Now, if you have multiple of these sensors, you can actually locate the shooter. If each of these sensors have multiple microphones, so a mini microphone array, and we have been building, let's say, arrays that are only, let's say, 3 inches aside, so 4 microphones, then you can also detect the angle of arrival of all of these events, basically the direction toward the shooter, because the sound arrives at those microphones at different times, and from those time differences, you can figure out the angles. Now, if you do all of these things and you have multiple of these sensors, you can locate the shooter, you can exactly identify the trajectory in 3D, you can estimate the speed of the bullet, the caliber of the bullet, and then even what kind of rifle it fired it. So that's just for interest that with these low-cost sensors, you can do lots of things with gunshot acoustics. Now, of course, for this project, the only interesting thing is the presence of a shockwave. So if a bullet flies close to the sensor, we want to be able to detect it that, hey, there was a gunshot. So that leads us to the overall concept of the system. So we want to integrate a shot detector into a GPS collar, and when a shot is detected, a shockwave is detected, we want to immediately send an alarm with the latest GPS tag that the device has. We don't want to wait for the GPS acquisition time, because in the meantime, they may destroy the sensors. But of course, we wake up the GPS, it gets a new location, so we can send an alarm with better position than originally we had that information. All right, so again, this slide just shows that we don't want to reinvent the wheel. So this unit is an add-on to existing GPS, commercial GPS collars. So optionally, they'll be able to integrate it into their system. And so our work only focuses on the board that detects the shot and then communicates this to the GPS collar. So this project started in 2007, a long time ago. So this is our prototype from 2008. This was for elephants specifically, so that's why this is kind of big. One kind of important factor that we actually used two different microphones. So a piezo microphone is attached to the wall of the sensor, and it's great to detect mechanical impact. So a mechanical impact may look like on the microphone similar to a shockwave, but with the piezo pickup and the regular microphone having those two different signals, we can actually fairly well distinguish between mechanical impacts and actual shock waves. And then also there is an accelerometer on that board, so we can also monitor the change in the animal's behavior after a supposed shot. We should see a change if it was a shot. If it wasn't a shot, then probably there wouldn't be any change. Now the prototype also had an SD card just to record these shots for further refinement of our detection algorithm. Of course, the final device will not have the SD card. So we tested the prototypes in various settings on cattle here in Tennessee, and the San Diego Zoo was nice enough so that we were able to deploy it on captive elephants for a couple of weeks. We had some deployments in Kenya and additional tests. So we gathered lots of data to be able to test the detection algorithm. This is kind of summarizing the findings. Oops. So you see on the scale, the detection output is probability from 0 to 1, 0 to 100% of whether this was a shot or not. And you can see that even this prototype from a few years ago was pretty successful in distinguishing gunshots from other natural noises, specifically animal sounds or mechanical impacts and other nature sounds. So that this gives us hope that this will work well. Again, this is a work in progress, so we don't have a final product ready to be deployed. All right, this is just summarizing various ways of detecting poaching, specifically with guns. And basically, I think our approach kind of hits the sweet spot. So for example, it doesn't only protect one animal. The shockwave can be detected reliably within 50 meters. So if there is a herd situation, then a single sensor can potentially protect the entire herd. Now, when I say protect, of course, there is a caveat, which is, of course, if somebody is already shooting at those animals, it's probably too late for that poor animal. But if the alert goes out and the rangers can come and catch the poachers, then, of course, it really helps the next animal they would have killed. All right, so summary. So I described this variable gunshot shockwave detector idea. So it's still a work in progress. Of course, it has to be low power, and we did various tricks to make sure that this can last for about a year, depending on lots of factors, of course. I mentioned that we are using the vibration and sound to make sure that the false detection rate is very minimal, because of course you don't want to call the rangers if there is no shot, because eventually they will lose interest in such a system. All right, so we are still working on this. We need to finish the new hardware design, update the detection algorithm with modern AI-based techniques to make it even better. We still need to implement this motion-based behavior classification after a detected event. And actually, we are working with Savannah Tracking out of Kenya to integrate this into their color at first. And of course, we need to test it. I like to make sure that everybody knows that this will be open source and available for everybody. So it's even though we work with a commercial vendor, the design and the software will be released so anybody can integrate it into their devices if they want to. All right, so that was the SHOT project, but I briefly want to talk about another project that is ongoing. So this is a National Science Foundation sponsored project started in 2023. So the goal here is to relate it to, of course, the shot detection, but build an intelligent acoustic bilogger. So a low power animal-borne acoustic data gathering device. So here you can see our current prototype. As you can see, it's very tiny. It's hardly larger than an SD card. And it has various operating modes. Of course, typically people have been using schedule-based, so you can just deploy it and specify when it should record and when it shouldn't. You also have a threshold trigger, so when it's completely silent, it's not going to just keep recording nothing. But more interestingly, there is this AI-based filtering and clustering method that we are working on. Basically, we are trying to identify events of interest and interesting events and rare events, and not fill up the SD card with detecting the same kind of noise over and over again. So this is an ultra low power design, so its power consumption is lower than MicroMoth, but it has much more processing power, which is actually nicely tunable depending on what you want to do on the processing side. And of course, a version of this will be used in the shot detector because it's much smaller and much lower power than the first prototype. All right, so this is based on the MBIC Apollo 4 MCU. It's an ARM core. Again, we are shooting for continuous monitoring for up to a year, but it depends on a lot of factors, on your battery size or your sampling rate, configuration settings, SD card size, well, the goals of the project, and so on and so forth. So the AI-based approach is an unsupervised clustering algorithm that will create these clusters of similar sounds. And based on the deployment, we can either record all those sounds or just keep statistics about the clusters and representative samples out of those clusters. You can also add an additional classification layer where you can specify whether you want to reject certain sounds. So for example, we can classify wind noise and not record continuous wind noise. Or if you are specifically interested in a certain animal call, then we can have a classifier that makes sure that all of those kinds of sounds are recorded and the clustering runs on the rest of the events. All right, so I think I'm gonna wrap up here because time is running out. I just want to show some ballpark power numbers on this last figure if you are interested. Thank you so much. Any questions?
Yes, we've got, first of all, thank you for that talk. That's super, super interesting. And we love to hear that shockwave detector project is open source because we love that. And like I think Frank mentioned in the chat, we're going to be having a meeting on funding and finance open source projects soon. So we'd love to hear about that. We've got a lot of questions in the chat and some time to go through them. So I'm going to pick a few out to just read. There's one from Nathan Harris. That's a question on the AI-based filtering that you mentioned, asking about what AI models they use, because it's interesting to be able to provide AI-based filtering based on the size of the device.
Okay, so it's not one of the traditional models for classification. It's specifically an unsupervised clustering algorithm. So it creates a lower dimensional space where it groups similar sounds together. And the part where we'll decide what to record and what to discard is still not implemented, but the clustering itself works very well. And again, the goal is to somehow let the domain scientists decide what they want to record. And if we have a cluster with thousands of events, we probably don't want to fill up the SD card and use all our power on that. So in that case, we'll just, let's say, store the metadata for those events and just some representative samples. But the goal is to provide a configuration interface before deployment time to specify all these requirements and automatically configure the software for that deployment.
Great, thank you. And then we have two questions from Carly. One about which we can address in the chat if there's like a website or contact information for Wiper, and also what the cost of the whole system is. And Carly, feel free to jump in. I'm not sure if you meant the shockwave detecting system or that second project that Akash mentioned.
So I mean, the cost will be similar, and I assume by cost you mean how much it takes or costs to manufacture one of those boards. I don't have exact numbers because right now we are just running prototype development, and of course, manufacturing 5 boards is almost the same cost as 200. So right now, I would say that the prototypes, let's say a couple of $100, but if we go up to a few hundred, batch of few hundred, it's probably going to be under $100 in hardware cost.
Amazing. And then there's another question from Nathan that I think was like a clarifying question that you mentioned that the microphones on the shock detector collars, microphones are only 4 inches apart and can calculate trajectory angle.
No,
Is
no,
that
no, no.
or no?
So that whole multi-microphone configuration was for just a general overview of what kind of things you can do with acoustic detection of gunshots. So this the shot detector only has a single microphone and the piezo just for helping with classification. So the only thing we can detect with that or with this unit is there was a shot, period. Okay, no location or anything else other than the sensor's location from the GPS color.
Got it. Yeah, it's a super fascinating project and seems like it has a lot of really incredible potential use cases. And I know we're right on time, so thank you so much for that great long talk. Feel free to keep putting questions in the chat for those who are listening, and then Akash can hopefully pop in there to answer them. So again, thanks everybody for joining our variety hour this month and for our speakers for their lovely presentations. I'm going to end the recording in just a few seconds, but everybody is invited, as always, to stick around for after hours to have a more casual conversation about anything that we heard today or really any other topic you could think of. So thanks for coming, and we will see you next month on April 30th. Bye.